Hello all, welcome to this series LLM Behind the Scenes. In this series we are going to look into the small concepts which powers LLM. Today we will look into transformers. So before we start, make sure that you set up your virtual environment, activate the virtual environment and install the required dependency into that. So to start with transformer, first let's understand what are vector embeddings. Let's suppose we have a word cat. Initially, we assign it a numerical value and it's a random representation like this. Then we have a dog and we assign it a random representation like this. And that is called as a vector representation of any token. Now there was a paper published in 2017, Attention is all you need. In that, a neural network architecture was presented, which is transformers. So what does it do is, initially you assign a random vector representation to any token, then you pay attention to the next token to it, and then you train on different sentences one by one and go deep. So once you do that, it will in the end understand. For example, let's take a statement: dog is an animal, dog is good animal, dog is common animal. So eventually it will understand dog and animal are related, and the weight it gives of dog and animal will be higher. Similarly, dog and bird are not related. It will not find any sentence where dog and bird comes together, or there will be rare sentences. So it knows that the attention of dog to bird is low, so the weight will be low. So again, to recap, initially all the tokens are converted into a vector representation, which is like a numeric representation. It's a multi-dimensional representation. Then after assigning random values, this transformer will give attention to its nearby one by one, and figure out the relationship between nearby tokens. Like dog and animal are strongly related, and cat is also most of the time is used in similar statements. So the vector representation of cat and dog will be close to each other. Okay, so then in this demo what we are going to do is we are going to use a BERT tokenizer, which tokenizes the given sentence, which is understood by this model, which is BERT model, which was developed by Google. It's an implementation of the transformers architecture. So we have an input like who loves cricket, and then we'll tokenize it. So in short, we can understand tokenize it like divide it into our words, and then we give it to that model and get the vector representation for those words like this. Okay, and at the same time we'll also have our dictionary or our knowledge. So we'll have two sentences in our knowledge: John loves cricket and Sam enjoys working on wicket. For that also we'll create the vector embeddings. Now these vector embeddings are mathematical representation of tokens. Because they are mathematical, it is possible to compute and get a representation which is very close to the my query vector embedding. So my query is who loves cricket, will convert into a number, and then we have this input knowledge of two sentences that will also get converted to a number. So we'll use a formula which is called as a cosine similarity, which internally uses a dot product of vectors. That will give me the distance of this and this from this vector, and the closest vector is my answer. So in this, who loves cricket is the query. We'll get the distance for this sentence and for this sentence, and we'll figure out that this sentence will have much more closer vector values to this sentence. And then in the end, we are going to use one library from NLP, which is Spacy. If you give any sentence to that library, it can detect the words, it can detect the entities, events from any sentence. So in this, we are trying to detect a person like who loves cricket. In this, we need John. So we give this sentence which we found very close to the query vector, to that NLP library, then that library will help us detect the person in that sentence, which is John, and then we'll return that John as the answer. So let's dive into the demo. First, let's import the required packages. So we are going to import the BERT tokenizer, BERT model from the transformers library. Then we'll use this function which gives the distance from one vector to another. So we'll use this vector, this mathematical function to calculate distance of our query vector to the our knowledge vectors. Then we have this torch, numpy and Spacy, the NLP library. So first we'll load the BERT model and the tokenizer. Okay, then model, then we define a function get embedding, which basically given any sentence. So this is the sentence, we tokenize it using the tokenizer. Then this tells us that we are using this model in a non-training mode. If we don't use this flag, it will internally do the back propagation, which is basically updating its layer based on what it trained. We don't want it to train, so that's why we are saying we are just using this model for inference. We'll get the output layers. So this output actually gives us embeddings per token, and in this we are going to do a mean and get the embeddings per sentence. So this gives embeddings per token. We are going to take the mean of all those and get one embedding per sentence. Now we have our knowledge base. So knowledge base will be two statements. John loves playing cricket, and the second statement is Sam enjoys working on weekend. Okay, and then we have our query, and we are going to ask who loves cricket. So now we'll create vector embeddings for the knowledge and the query. So let's first create knowledge embeddings. Okay, so for each sentence in the knowledge, we are just going to create the vector embeddings and convert it into a numpy array. Then we create the vector embeddings for the query, and then we found out the distance. So yeah, we are using this cosine similarity for calculating the distance of query embedding to every knowledge embedding. Okay, so this will return me an data structure which has index of the knowledge embedding and the distance to it, and then we want to then get the most closest embedding. So for that we'll use the argmax. So argmax will actually give me the index of the knowledge embedding which is most closest to the query embedding. Then now we got the index, so we found out the chunk from the knowledge or the sentence from the knowledge, and then after we find out that sentence, we use the Spacy library, which is an NLP library for English, and then then we parse using that library. That library will identify different entities, and for person it will identify the entity and label it as person. Then we are going to print that. So if there is a person, we are going to print that. If not, we'll just print the sentence. Person entities and person entities of 0. So before running this program, ensure that you have installed all the dependencies, and also you have installed this Spacy for English, otherwise it will not run. And for all the dependencies you can actually just install from the requirement.txt. Let's run this demo. Expected answer is John, right? And suppose we don't use this Spacy, and don't detect this person, it will give actually answer like this, and it will basically the most closest vector to the query vector, and that will be the complete sentence. That's it for this video. Thank you.